Hi everyone, let us continue with examples on topology. So to begin with, let X be a set and define tau to be what? 2 to the power x, basically power set of x. Now, you can clearly see that this is a topology on set x, right? So then, x along with this topology is known as discrete space. Fine, or discrete topological space. Now, the question is this metrizable? Is above space metrizable? I hope you know the answer. So I'm not gonna prove it. I'm just mentioning which metric you should have and a fact which would be very useful. So answer, yes. So which metric? The discrete metric. And another thing which I said I want to mention which would be useful. So for any set, say capital A in X, how you can write capital A? You can write it as union of its members, right? Singleton X, X is in A, right? That's what you can do. So using these things and whatever we have discussed about discrete metric, you can argue that this space, discrete space, is indeed a metrizable space using discrete metric, of course. Good. Now let us proceed further. As you all know, in group theory, for example, when you talk about subgroups, or in vector spaces, when you talk about vector subspaces, you are always interested in constructing new examples out of the given spaces or subgroups, right? So similarly, and how you do that, if you remember, using the operation unions and intersection. For example, intersection of subgroups or vector subspaces is a subgroup or vector subspace. Similarly, union, you cannot say about this thing about union, right? Union need not be a subgroup or a vector subspace. So on the same lines, we have similar analogy here. So let me write it as a whatever remark or something, as a note. Let X be a set and tau alpha in some index set, say capital lambda, be the collection of topologies on X. Note that I am not saying collection of all topologies, some collection. This capital lambda is in some index set. Okay? So what's our claim is? Claim 1. Union of tau alphas need not be a topology on X. Second, intersection of these tau alphas is our topology on X. And we will be using this second thing later on. I'm not gonna disclose right now, but in the concept something called subbases. Okay, so we have these things. Let me give you a hint for the first claim. You can use Sierpinski's space to argue first. And second is, you have to show it by definition. So if you want to try on your own, stop the video, try it, and then you can match the things after you are done. So let me proceed. Now, for first, define tau 1 and tau 2 to be, so how I am defining this, phi singleton A X, and this is phi singleton B X, where, what is X we should specify, right? Where X is A, B, C. These are three distinct points. So what kind of topologies you are considering? Sierpinski's topology. I hope you have googled about this and you might have seen beautiful fractals like Sierpinski casket. Okay, I will come to that maybe in some special lecture. So observe that tau 1 union tau 2, which is phi singleton A singleton B X, is not a topology. On what? On X. Right? You should be able to argue this. I'm leaving it for you guys. What you have to see, which property is this union doesn't satisfy, right? Now let me begin with true, second one. I would like you guys to verify the first and third property in the definition of topology. What is the first axiom? That phi and X should be there, and the third one is, or second one, like it doesn't matter, right? One I will do, the other two you are gonna do. So please verify first and second. Let me do the third one. Okay, what I mean is, I am gonna prove that this intersection tau alphas is closed under arbitrary unions. So let me begin. So let G beta in theta be a collection of members or elements in where intersection tau alpha. What we want to show is topology. What we want, the union should be here, right? That's what I am doing, the third property. I have written in that sequence. So let me begin with that. So what it means, guys, it means G beta belongs to intersection tau alpha, alpha in capital lambda, for every beta in theta. Good. What this implies, G beta is an intersection of tau alphas. It means it is in each and every one of them, right? The meaning of intersection. Okay. Now, what we are gonna do, look at these two things. This and this. What is tau alpha? Tau alpha is a topology in which these g betas are, right? All of the g betas, where beta is coming from theta. So what it means, guys, this is a topology. So it will have arbitrary unions. So union g beta, beta in theta, this is in tau alpha. But this alpha is also arbitrary. All of the tau alphas are topologies. So what should I write here? For every alpha in capital lambda or omega, whatever you want to use the symbol. Fine. So what it means? If it is in tau alpha for every alpha, it means it is the member of intersection also. That's what we wanted, right? So please complete the other two properties. Those will be on the similar lines. Why I have chosen this? Like, just I want beginners to learn the way to write mathematics. See, you may understood everything or you may have intuition, but if you are unable to write it or explain it to someone on board or on like the recordings I am doing, I am not talking about the accuracy of your conversation, I am talking about the accuracy of mathematical logic. So if you are not able to do that conversation and write, then it means you haven't actually understood it. That is what I believe. So that is why I am focusing on the little details also. So now let me proceed, guys. Let us have a remark. Remark. I want you guys to do your hands dirty, huh? I mean, do some kind of permutation and combination, and at least do these things. So let x be a finite set, and okay, no and, find the total number of possible topologies on X if number one, okay, just write in here only, if cardinality of X is 1, 2, 3. Also, I want you guys to Google these things. What happens if increases? You will see a huge difference between, from 3 to 4, 2 to 3, 4 to 5, 6 to 7. So let me have the first open problem which you can talk about here in topology. We will be discussing a few of them as far as we will go in depth. This problem is very simple to understand, but trust me, it is one of the most challenging and difficult problem, because people have used complicated logics and computer algorithms to answer this thing for particular numbers, like little bit of big numbers, 2-digit number and all. So In general, we don't know this question. What question? Given a finite set of cardinality n, what is the total number of topologies on X? So this is an open problem. One may discover some solution of this, but like it is very difficult. There are some special topological spaces which we will be studying. We call them Frichet spaces. For Frichet spaces, we have a formula using something called Stirling numbers. That I will tell you later on. I'm just mentioning it for now. So using Stirling numbers, I'm not gonna do that because trust me, I also don't know how to do that. I mean, I haven't looked into the argument, but yeah, Stirling number is something which is associated to combinatorics. So let me continue. What I want to discuss now is some properties of closed set. You remember what is a closed set in a topological space? If its complement is open, right? Or if its complement is a member of topology, is in topology. So I'm not writing it again, that's why I have verbally spoken. So what I want to have here, result. Let X tau be a topological space. Fine. Then we have three things. Number one, phi comma x are closed in X with respect to, of course, the topology tau. So if I am not writing with respect to tau, of course I am working with the given space I have assumed above, x comma tau. So you may write it or you may not write it. But when you have involvement of 2-3 topology at a time, then you should be very precise, right? Where a set is open, right? So we will come to these things later on also. So second, finite union of closed sets is what? Closed. You see, it's like the one you might have done in metric spaces. Third, arbitrary intersection of closed sets, of course in X with respect to tau, is closed, right? So these are the three things, and I request you guys, please try first and third. I will do second. So what you have to assume, what should be our hypothesis? Let F1 and F2 be closed in where? X. Of course with respect to the given topology tau. I am not writing it because I am dealing with a particular space. Only one topology associated with that. So what it implies, guys? The complements are open. Or in other words, these are in where? These are in tau. What this implies? This implies their intersection is also in tau, because tau is a topology, hence it is closed under finite intersections. Right? Now what this means? This implies X minus F1 union F2 belongs to tau. Why? Again, De Morgan's law. I'm sure you haven't thought about this in 12th class, that this is gonna be very useful in 12th year or maybe in 11th class, whenever you have studied this. So what it means, the complement is open, so this implies F1 union F2 is closed in X, of course with respect to tau. Very nice. So using these remarks or result about closed sets, let me give you an alternative way to define topology or topological spaces. Alternative way to define a topology. Although we are not gonna follow this particular convention, we will be using the main definition only, what we have done initially. But why I am telling you this, because this is important, and because this is important, I will mention one example also. So let X be a set. We say tau contained in 2 to the power x is a topology on X if, number 1, phi and x should be there. Very nice. Number 2, tau is closed under finite unions. Number 3, tau is closed under or with respect to arbitrary intersections. So that is how we define. So you see, associated with this, the definition of closed set is gonna change, right? A set F contained in X is closed if F belongs to tau. And what would be the open set in this case? The complement, right? Basically a set is open if its complement is closed. So you see, this is purely like some sort of an analogy of the main definition. So this is another way to define. So what I want to say is, this is important, and you will see this when you will study Zariski topology. You're gonna encounter this topology in algebraic geometry. I'm not gonna tell you anything about this right now. Maybe in some another special sessions. I'm planning to do special topics also, but after covering good amount of material on topology, I'm gonna discuss about some special things. But yeah, I will be mentioning few of the applications of topology which I have studied in various other branches like Galois theory, algebraic geometry, or algebra, linear algebra, and at various in analysis at various other places. So I would be mentioning those. Maybe the discussion I will not be doing that we can take as some different session, or sometime maybe when we have a good knowledge of topology, because my first aim is to cover sufficient amount of topology. So let me add this in a box. I mean, no need of using this definition in this particular lecture series. So it's a way to define. We should know these things. Okay. I want to give you one more remark about these open sets and closed sets, and then we will end this session. So, remark. The two English words open and closed are actually not opposite of each other. What I mean by opposite, I mean antonyms. I don't know the spelling of this word antonym, that's why I have written opposite in, I mean basic English. So these are not opposite words, right? Because see, there are sets which are both open and closed. We have seen in fourth space, phi and phi empty set and the whole space is another example. And in the next session we will be seeing many examples, the sets which are neither open nor closed, the sets which are closed but not open, the sets which are open but not closed. So we are gonna see these examples, and why I'm planning to have a separate session on these examples, because you see many a times you have a picture and a very good visualization of things, but when it comes to write down, that is something really we should learn. And trust me, our understanding of a concept is clear only when we know how to write it, since this is mathematics. So thank you very much. We will meet in another session. Take care and bye.